Today I'm going to present our work, VidLanKD, Improving Language Understanding via Video-Distilled Knowledge Transfer. Before we get into details of our work, let me first introduce the preliminary task, language pre-training. We currently learn language understanding with language pre-training methods that we first train a backbone model on large language corpus with language model tasks. We then fine-tune this backbone model on small downstream tasks, and it shows improvement over the directly trained models. But humans learn language by listening and speaking. Visual pointing is an essential step for most children to learn millions of words. Therefore, Hao and Benzo proposed to supervise language model with visual grounding. Vocalization visually grounds a language model with vocals from a text-image alignment model. It is essentially a method of knowledge distillation. But there are two caveats: quantization error that finite images cannot represent diverse concepts, and the issue of static images, which cannot represent motion or action. Therefore, we introduce our work, VidLanKD, Video Language Knowledge Distillation. Similar to vocalization, we first pre-train a cross-model language model on the video dataset. Second, we transfer its knowledge to text-only model on the text dataset. Then, let's get into the details of our method. We train our teacher model on the multi-model dataset with two objectives. The first objective is video language contrastive learning. We first obtain the average food video representation from video encoder. Then we obtain the positive and negative text feature representation from the teacher model. Positive representation means text aligned with video. Negative means text not aligned with video. We use the resulting features, visual features and text features, for triplet margin loss. And here is the detailed implementation of triplet margin loss. The second objective of teacher model is math language modeling, which is commonly used language modeling objective. After discussing teacher model, we then introduce our student model and knowledge transfer method. We train our student model on a text dataset with two objectives. The first objective is math language modeling, and the second objective is knowledge distillation for the teacher language model that is frozen. Concretely, we input the same text to teacher and student models to obtain hidden feature representation outputs. Then we transfer the knowledge from teacher model to student model through this hidden feature representation by some knowledge distillation objectives. Here are some KD objectives we use. We have mean squared error, soft label, neuroselectivity transfer, and contrastive representation distillation, which can all be referred for their details in the paper. In the KD process, we introduce an MLP distillation head on top of the last hidden states of the student model, which means we transfer knowledge from teacher representation to student's hidden representation mapped by an MLP. We find that adding a distillation head slightly improves the distillation performance. We then introduce our video text and pure text datasets. We use How-to-100M for cross-model pre-training of our teacher model. It has 1.22 million videos, totaling 136 million video clips, with total duration of 134 hours, describing over 23K different visual tasks. For text dataset, we follow localization to use English Wikipedia. There are 29 billion tokens and 120 million sentences in English Wikipedia. We show our method's performance on language understanding downstream tests, ranging from glue, squat, and swag. The model scale we use is BERT 12 layers. found that video recognition performs better than image recognition. Moreover, VidLanKD method with objectives, NSD and CRD, performs the best, meaning better than recognition. We thus show other downstream task performance that is more physically and visually related. We found that our method largely improves glue diagnostic subcategory, knowledge, common sense, versus other subcategories that are pure language understanding, like lexicon, predicate, or logic. Our model largely improves performance on PICA, a physical common sense reasoning dataset. Here are some examples where our method improves over the text-only baseline and answers correctly on these physical common sense examples. Moreover, our model largely improves performance on tracing, a textual temporal reasoning dataset. Here are some examples where our method improves over the text-only baseline and answers correctly on these temporal reasoning examples. After discussing downstream task performance of our proposed method, we then show several ablations based on the datasets, pre-training methods, and model components. We first show pre-training on different text corpus and found that pre-training on Wiki performs better than no pre-train and HOT 100M. This establishes the need to leverage Wikipedia and knowledge transfer, and visual supervision improves language understanding on Wikipedia. I also show student performance on downstream tasks with distilled knowledge from different teacher models. First, the teacher model trained only with MLM, and the teacher model trained only with visual supervision. Both performs worse. The teacher model trained both with MLM and video supervision. We also show results for student performance with KD from different strategies. Text PD refers to model trained only on Wikipedia. Video PD refers to model trained only on HOT 100M with video supervision and math language modeling. Two-stage PD refers to model first trained on HOT 100 million with video supervision and math language modeling, and then trained on Wikipedia. VidLanKD refers to our knowledge distillation method, and we easily found that our method performs the best. We also show the performance of different KD objectives and found that NSD and CRD performs well, and their combinations performs the best. We also show further ablation that KD performs better than recognition for image grounding and visual grounding. Video knowledge supervision performs better than image knowledge supervision for recognition, and also KD. After ablation studies, we further show our method's performance with video text retrieval on teacher and student models. Note that students don't see videos at all during training. For the query, the expansion of agriculture, commerce, trade, and transportation between civilizations in different regions offered cooks many new ingredients. Both our teacher and student models can retrieve videos related to food making, cooperation, and ingredients. For the query, as an outcome of these changes, craftspeople today increasingly make use of semi-finished component or materials and adapt these to their customers' requirements or demands. Both our teacher and student models can retrieve videos related to crafting, materials, and service-related images. Thanks for listening. Feel free to ask questions to me. The code is available at the given link.